no boundary proposal of the universe. Did the universe have no beginning? What if the Big Bang wasn't the abrupt birth of time, but the smooth opening of a four-dimensional cap with no edge? The no boundary proposal, put forward by James Hartle and Stephen Hawking, imagines the universe's origin as a finite yet boundary-free geometry, akin to the North Pole on a sphere, where time behaves like an extra space dimension and there is no point at which physics breaks down. What exactly is the no bidi proposal? Is the idea that in the universe's earliest quantum era, space-time was entirely smooth and without singularities. Instead of a sharp beginning, the cosmos resembles a closed surface with no boundary, emerging naturally from its own geometry rather than from a mysterious before. How can time act like space at the beginning? At the extreme energies of the quantum gravity regime, the distinction between time and space blurs. One direction that we call time in our world plays the role of a spatial dimension in the primordial era, allowing the universe to round off smoothly rather than starting with infinite curvature. If there's no boundary, where does the universe come from? In this view, the universe doesn't spring from nothing, but crystallizes out of a self-contained geometric state. There is no before, just a compact four-dimensional shape that transitions into the expanding, time-driven cosmos we inhabit. Can we test a boundary-free cosmos? Clues may hide in the fine-scale patterns of the cosmic microwave background, or in the spectrum of primordial gravitational waves. If observations match the statistical imprints predicted by a no-boundary quantum wave function, we'd glimpse evidence of a universe born from geometry, not a singular event. Why should beginners care about a universe with no beginning? Because it shows science can tackle the most mind-bending questions, what happened before time, with bold ideas that challenge our intuition, revealing that the cosmos may be a self-sufficient masterpiece of geometry rather than a creation, ex nihilo. The no-boundary proposal posits that the universe has no singular starting point or abrupt edge, but instead emerges smoothly from a compact Euclidean geometry. Near what we conventionally label as time zero, time itself behaves like a spatial dimension, transforming the apparent origin into a rounded cap rather than a singularity. In this view, the quantum wave function of the universe is computed by summing over all boundaryless compact four-dimensional geometries using a Euclidean path integral. This reframes the Big Bang not as a catastrophic beginning, but as a quantum transition from a timeless, smoothly connected state, much like a perfectly round hill flows naturally into a sloping meadow without a sharp summit. Space-time itself glides seamlessly from a Euclidean domain into an expanding universe. In contrast to classical cosmology, where the Big Bang is modeled as a singularity, where space-time curvature and energy density become infinite, the no-boundary condition replaces this problematic feature with a finite, non-singular geometry. Rather than an abrupt temporal beginning, the early universe is imagined as a smooth, four-dimensional sphere where spatial and temporal dimensions interchange roles. There are no boundaries at this origin, no edges to impose arbitrary conditions, only a cap that transitions gently into real-time evolution. Instead of geodesics terminating at infinite density, they continue smoothly across the Euclidean to Lorentzian bridge, like a sharp cone tip being replaced by the gentle dome of a hemisphere. Quantum cosmology provides the framework for understanding this proposal by treating the universe itself as a quantum object, described by a wave function that satisfies the Wheeler-DeWitt equation without relying on an external time parameter. The no-boundary proposal constructs this wave function by evaluating a Euclidean path integral over all compact metrics and matter field configuration. Each geometry contributes with a weight determined by the exponential of its Euclidean action, favoring smooth minimal action histories. Near the Planck scale, quantum fluctuations dominate over classical trajectories, and the most probable histories are those that start from compact, non-singular configurations. It is as if every possible origami fold is considered, and the universe selects the most natural unfolding into an elegant crane. The essential mechanism behind this smooth emergence lies in rotating real-time into imaginary time via a Wick rotation, transforming the Lorentzian gravitational action into a Euclidean one suitable for convergent path integrals. In this imaginary time regime, geometries are smooth and compact, avoiding the singular behaviors that plague real-time general relativity at small scales. After summing over these Euclidean configurations, analytic continuation restores real time, producing an expanding space-time that looks inflationary at early times. Much like baking a cake in a spherical mold before slicing it open to reveal the continuous fluffy interior, the early universe is shaped in a compact domain before transitioning into familiar, expanding space. The geometry and topology of the compact manifold critically determine the observable properties of the universe. A simple four-sphere topology enforces homogeneity and isotropy, minimizing primordial anisotropies. Slight deviations from perfect symmetry, small ripples or distortions in the Euclidean capside, small ripples or distortions in the Euclidean capsidries of inch topologies and curvature properties correspond to different spectra of density perturbations and gravitational waves, directly linking the hidden geometry to the large-scale structure of the cosmos. Just as tiny imperfections in a glass mold shape the scattering of light through a finished chandelier, minute geometric features imprint themselves onto the observable sky. Quantum fluctuations around the compact instanton are responsible for seeding primordial density in homogeneities through nonlinear couplings in the gravitational and inflaton fields. When these fluctuations are analytically continued into real time, they become the initial seeds for cosmic microwave background anisotropies and the formation of galaxies. Nonlinearities amplify certain modes, leading to a slight deviation from exact scale invariance in the primordial power spectrum. The resulting pattern of structures in the universe can be traced back to the interplay of quantum jitters and the smoothness of the underlying compact cap. Much like ripples on a pond freezing into specific crystalline patterns that later guide crack propagation in ice. One of the profound strengths of the no-boundary proposal is its natural affinity for inflationary initial conditions. The most probable geometries under the no-boundary measure are those that initiate slow-roll inflation, providing a quantum origin for the rapid early expansion that solves the horizon, flatness, and monopole problems. Rather than assuming special initial conditions for inflation to start, the no-boundary proposal shows that inflation emerges from the most probable class of quantum histories. In simple scalar field models, no-boundary amplitudes peak for field values that naturally produce 50 to 60 e-folds of expansion, like a ball placed at the top of a gently sloped dome whose most probable descent naturally traverses the steepest corridors. Testing the no-boundary proposal remains a formidable challenge, as its central predictions concern Planck-scale phenomena far beyond direct experimental reach. Subtle differences in the predicted spectrum of cosmic microwave background anisotropies, especially in B-mode polarization patterns and tensor-to-scalar ratios, offer potential observational handling. However, the theoretical foundation itself, the definition of the gravitational Euclidean Path Integral, is not yet fully rigorous, introducing ambiguities. Much like trying to reconstruct a chef's secret recipe by tasting faint traces of exotic spices hidden deep in a complex stew, probing the fingerprints of a boundaryless origin demands extreme observational precision and robust theoretical extrapolation. Future directions involve combining insights from non-perturbative approaches to quantum gravity, such as holography, loop quantum cosmology, and string theory, to better define and compute the no-boundary wave function. Precision cosmological missions targeting primordial gravitational waves and spectral distortions could refine or constrain the proposal's prediction. Moreover, new mathematical techniques for classifying and summing over compact topologies may offer ways to sharpen the measure over initial conditions. If ultimately confirmed, the no-boundary proposal would recast the question of why there is something rather than nothing into a geometric principle, replacing singular origins with smooth quantum spacetime architecture. Much like discerning the contours of an unseen landscape by studying its reflection in a pond, the geometry hidden behind the early universe could reveal itself through the faint patterns left on the cosmic canvas.